So, essentially what we're going to do is a significance test. Significance test about mu. Hey, if we're going to check conditions about mu, so right, always the first thing we're going to do, we're going to name our parameter. We're going to make a hypothesis, but we're going to have to check conditions. So obviously, for our S, we'll want to know that it's a simple random sample, right? And then, I mean, this doesn't change at all, right? We need to check the 10% rule, right?
Do you go for every test at all? Okay. Apparently that's what it entails, I guess.
VI goes without saying. In this case, each trial is definitely independent. But the N is where things change. With the proportion, we had to check that N times P was greater than or equal to 10. And we had to check that N times 1 minus P was greater than or equal to 10. Now, it's good enough. If you get this going on, you're pretty golden, right? You can say sample size is large enough. Just assume that it's normal. But what happens if N is less than 30? If N is less than 30, we have to look at the distribution. Same as we did in 8 to do confidence interval. Look at the distribution to assess the normality. So let's look at an example where we would have to check this out. Okay, so classic rock radio station claims to play an average of 15 minutes of music every hour. However, it seems that every time you turn to this station, there is a commercial playing. What? To investigate their claim, you randomly select 12 different hours during the next week and record what the radio station plays in each of the 12 hours. Here are the number of minutes of music in each of these hours. Right? So let's go ahead and check the conditions for this thing. First of all, S, the data comes from a random sample. Or we could just say an SRS. The what? The data. Wow. Okay. We're just going to say each trial is independent. Independent? Maybe not. Let's check for normality. Hey, N is not greater than or equal to 30. In fact, N is 12. Right? So, we have to assess normality in a different way. So I'm going to have to put this data into my calculator and then analyze the distribution this way. I'm going to show you a couple ways to assess normality. And they're all quite cool. Or useful, I should say. So if I'm going to enter data, I'm going to have to make a listen spreadsheet page, right? And I'm just going to call this, I don't know, I'll call it radio. That's what we're dealing with. Go ahead and follow along and do this, please. I did it again. Okay. 44. 49. 45. 51. 49. 53, 49, 44, 47, 50, 46, 48. Always check when you're done putting in your data. If there are 12 entries, I should be on 12, right? That's a good way to check to see that you didn't miss anything or enter anything twice. If you're not on 12, you should check for those things happening. I'm going to go ahead and put that data on the board because I know not everybody got that in. So there you go. So we will go back to our calculator. Now we're going to hit doc. Ready? Doc. Insert. And now we need a data and statistics page. Then I go ahead and add the variable radio. I don't know. It looks okay. Yeah, I don't see skewness if I look at this graph. Guys, the easiest graph to put on here to show that you don't see skewness is going to be a box plot. So let's go ahead and change this to a box plot. If you are having to look at the graph of the distribution in order to assess normality, the easiest graph to put on your paper as an answer is a box plot. Alright? You are going to need to provide some evidence. You can put the dot plot on there, and from this dot plot, it looks like there's no skewness, right? There's no obvious skewness. It doesn't look like there are any outliers. This doesn't look like any, very abnormal data, right? It looks like we could go ahead and assume normality so that we could do a t-test. But I don't know. I don't think this is very awesome to put on a test. And the recommendation that very experienced teachers have given me is that you put a box plot on your test for the AP. So that was the recommendation. So and it's as easy as copying the thing down when we make this a box plot. So we hit menu. We go to plot type, and we choose box plot. No outliers. It doesn't look very skewed. It's good, right? If I have the box all kind of crumpled up and crimped way over here on the left side, and a big old long line over here, might be a little skewed. right? You should be able to assess skewness by looking at a box plot. But I don't know. For some reason, this is the recommended plot to put on your test when you're having to assess normality. You could say, from the box plot, I do not see any skewness in the data. We can assume normality and go ahead and carry out a t-test. Okay? Another one that you can look at, though, that is also helpful, if you're not sure if it actually is, you can go to your normal probability plot. So go to Menu, Plot Type, Normal Probability Plot. If your plots roughly follow that line, then you can also assume normality. Right? So you could write on your test, I looked at a normal probability of the plot, normal probability plot of the data. It looked to be approximately normal, and then draw the box plot, whatever, and you know what I mean? You can do a bunch of different things. It's really nice to include a graph, though. Some sort of graph of the distribution to say that you did actually look at it, not just to say, I put it on my calculator. All right? Okay. So we can say, I will actually go ahead. Okay. So we'll copy this down. 40. Cool. The box plot of the distribution does not show any obvious skewness or outliers. We will assume normality. Okay. Next, we're going to look at calculating a test statistic for inference on a sample mean. Our test statistic for tests about a sample mean is going to be t now. And remember, it's always our statistic minus our parameter, right? So that'll be x bar minus mu sub naught, sub 0, mu naught degree. And what is our statistic that we use? It is sigma divided by square root n. Sorry. And then if you don't know it, right, or as you were saying, right, sometimes you'll be given the population standard deviation, but more often than not, it'll be S sub x, the standard deviation of the sample, divided by the size of the sample. I want to show you where to find this on your formula sheet. Where is it on your formula sheet? If you go to the other side, it's right here. Always, your test statistic is going to be written there. Statistic minus parameter divided by standard deviation of your test statistic. And it has, actually, your standard deviations as well. Right? So for sample mean, there it is. For sample proportion, there it is. You don't have to memorize those, although you probably already have them memorized. The good news is they get more complicated when we get to two sample means, or two sample proportions, and then a chi-square as well. So that's it. But that's where you find this stuff. It's on that back sheet of your formula sheet. Okay? All right? Let's go ahead and put this into motion. Let's see. And sorry, this looks pretty bad. I'll make it look better. We're going to test our null hypothesis that our mean is equal to 50 against our alternative hypothesis that the mean is actually greater than 50. Let's go ahead and we're not going to go through the entire process of inference. We're not going to go through phantoms. We're just going to compute the test statistic and p-value. First thing I'm going to do is calculate it on my calculator, and then I'm going to put all my stuff in my formulas. So I'll go calculator, then write all the formulas down, and then write my p-value. Here we go. We're ready? Oh, no. Let's get out our calculator. Here we go. So, I'm going to go ahead and do this on the scratch pad. I don't want to deal with what we were dealing with before. Oh, no, my bad. I don't want to do it on the scratch pad. Silly me. Let's go ahead and get out our calculator because the data's already there. I called it radio. Let's go ahead and insert a calculator page. You can do it. Okay. Why? All right, on this calculator page, we will go ahead and actually carry out our test. So I will hit menu. Statistics. Do follow along. Okay, there I have inserted the calculator page. I Do what? Menu statistics. We need to go to stat tests. What test do we need? It is just a t-test. That's it. We go to t-test. We're going to use data. So we do have the choice of using data or statistics, right? We have the data, so we're going to use data. What did we say that the mean was for our? We said 50, right? Our list we choose will be radio. We don't change that frequency list. Our alternative hypothesis, though, we will have to change. And we think that mu is less than? Yeah. I do not know why this is not working very well. Alright, here we go. We have our test statistic. We have a p-value. Our degrees of freedom. We know what x bar is. It's amazing. The reason why we did that all at once was because all of these values are values that I have to plug into the formula, right? Already pre-calculated for me. So that's why I go to the calculator first. You can calculate all these things with your calculator and then do this test and you would be doing double work. I'm trying to be efficient as well. So, let's fill in our formulas. And I'm going to have you guys actually shout these out because I have to go to a different screen. So, T is equal to, what is x bar? 9167 minus 50 divided by, what is the standard deviation? Is it there? No? Yeah, it is. There it is. S of x, 2.811. Divided by the square root of 12, which turns out to be approximately what? What is our test? What is t? Okay. There, we got our test statistic. Let's get a p-value. So using our notation, we want to know the probability that I believe that's not correct. Okay, we'll just use t. Well, we're looking at the probability that t is, well, let's draw a picture first before we can determine. It's kind of nice to draw a picture. There's our mean. So we're looking at this, right? This is actually 2.5674, right? So I'm actually looking at the probability that t is greater than 2.5674. And we're using degrees of freedom equal to 12 minus 1, or 11. This probability has been given to us by our calculator, and that is 0.013. Approximately 0.0. My answer is a little bit more robust than the one that the book gives. I included a picture.